Welcome. Now we're going to continue the topic of the previous video. We want to look at the calculation of capacitance. This is where we imagine we put a capacitor together, the plates, the dielectric, etc., and see what value we get for the capacitance. Remember, capacitance, the ability of this thing to hold charge, and it's charge per voltage. Okay. Here's the formula for capacitance. Remember that kappa, the dielectric constant, the ability of the material between the plates to polarize and partially cancel the electric field that's caused by the charge on the two plates. This epsilon is a constant. We're going to look at that. A is the area of the plate. There are two plates, so it's the area of one of the plates. We'll always assume the two plates have the same area, the area of either one of the plates. D, the distance, the separation between the two plates. You see, to get a large capacitance, which means a large amount of charge per volt, you want a large area. Remember, you're putting charge on those plates to change the potential of the plate. You want D to be small. The smaller D is, the more the positive and negative charges can tend to stabilize, and you can put more on there. And kappa, that dielectric constant, the ability of that dielectric to polarize. Now here's this constant that goes in the middle. It's just a number. It's not one that's especially easy to memorize. You just want to have it available, that you can plug it into an equation as needed. It's called the permittivity of free space. And units are not particularly insightful, Coulomb squared per Newton meter squared. But we'll work the problem, we'll plug it in. We'll use this constant. Warning, do not confuse C with C. What do I mean by that? Look at the top. The first equation, we're calculating C, the capacitance. Now, in this last definition of the constant, we have, as a unit, Coulomb squared. Yes, we're using this capital C twice in the same context. Once to stand for capacitance, once to stand for Coulomb. You have to be able to sort it out from the context. We do this routinely with millimeter. Millimeter, you have M. The first M stands for milli, 10 to the minus 3. The second M stands for meter. So we see millimeter, we understand the two M's are different. Here we have to treat it the same way. We're calculating capacitance, that's capital C. We have a unit, Coulomb is also capital C. Constant. This, I think, is especially interesting if you studied a little bit of chemistry, especially organic chemistry. Now, maybe you have, maybe you haven't. It's not required for this course. I just want to give you a little bit of insight or application into the material we're studying here with what you may see in another course, such as chemistry, organic chemistry, maybe biology, biochemistry. Dielectric constant. The ability of this material to polarize and have an electric field, which is going to partially offset the field of the two charge plates. Air has a value 1.0. It's actually slightly different. A vacuum is exactly 1.0. Air is just slightly different because there are some oxygen, nitrogen molecules, etc., but they contribute very little polarization. What about paper? Well, paper has a value 3.7. Now, paper is largely made of cellulose, carbon, hydrogen, oxygen. So you've got a little dipole moment built into the molecules. Paper is going to be a rigid molecule. It's not going to be able to reorient, but you can probably imagine distorting the electron clouds of the molecule and inducing a little dipole moment. And so you get a little bit of polarization when you put it between the plates of a capacitor. What about things that are free to move? Isopropyl alcohol. Molecule has 3 carbons with a hydroxyl group, OH, in the middle. Small molecule, low viscosity, can reorient. Now we have a dipole moment, a dielectric constant, much larger than paper. Another molecule that's similar, acetone. 3 carbons. Instead of a OH hydroxyl group, you have a C double bond O. Pretty close to isopropyl alcohol. If you put those molecules, the structures side by side, you'll see a lot of similarities. 3 carbons, oxygen in the middle, or off the side of the middle. Ethanol, you have 2 carbons and a hydroxyl. So this is more polar because you have the hydroxyl, the larger part of the molecule, larger dielectric constant. Methanol, a single carbon with a hydroxyl, larger dielectric constant. Water, you have, of course, just a hydrogen with a hydroxyl, much larger dielectric constant. You don't need to understand organic chemistry for this course. You don't need to memorize these numbers. This is to illustrate how what we're learning here may apply to another course you might take. Hopefully you find it of interest. These molecules, there's some induced polarization of distorting electron cloud, but you see these liquids can reorient and have the dipole moments line up somewhat with the field of the plates, and then you have larger cancellation of the field and a larger capacitance. Okay, let's look at a typical problem. Let's consider a homemade capacitor. Let's say you construct a capacitor using aluminum foil for the metal plates and a piece of copy paper. So that copy paper, out of your printer, your copy machine, whatever, has a dielectric constant 3.7. By the way, there's no unit on that dielectric constant. It's a ratio just to multiply what you would have if there was only vacuum between the plates. Okay. The paper has a thickness of 0.1 millimeter, typical thickness of a piece of copy paper, and the size 28 centimeter by 21.5 centimeter. If the aluminum foil is cut to the size of the paper, of course you have 2 pieces, what will the capacitance be? Go to the whiteboard. Okay. I like to go step by step because then it's easy to go back and check my work. First thing, when I do this correctly, what is D, the separation between the 2 plates? 0.1 millimeter. Milli is 10 to the minus 3. So 0.1 times 10 to the minus 3 meter. Area. 28 centimeter by 21.5 centimeter. Centi is 10 to the minus 2, the same as dividing by 100. So you want to convert them before you multiply them. Make sure you get the right powers of 10. The 28 becomes 0.28 because centi is 10 to the minus 2. The 21.5 becomes 0.215. You multiply that out, you get 6 times 10 to the minus 2 meter squared. Meter squared. We convert them to meter before we multiply them. Now we plug into the formula. Let's look at this formula again. The 3.7, that's the dielectric constant kappa. Here's his other term. Here's his epsilon 0, 8.85, 10 to the minus 12. There's a unit, Coulomb squared per Newton meter squared. On the left-hand side, C is capacitance. In the unit, that C stands for Coulomb. The area of the plate divided by the separation. So there we have the 602 to the minus 2 meter squared, 0.1 to the minus 3 meter. Okay, you can rearrange it or plug it in your calculator, however you like to do it. You come up with this right here. Now those units, if you look back, the meter squared cancels meter squared. Your unit is going to be Coulomb squared per Newton meter. Okay. You're not going to, nobody's going to remember how to convert the unit. But we're calculating capacitance. The unit is farad, capital F. So I've converted the milli, I've converted the centi. I know I've got the right unit, so the answer has to be farad. Capacitance 1.97, 10 to the minus 8 farad. Now, if you ever go into the lab, go into the electronic shop, pick up a capacitor, I've never seen one that had scientific notation listing. They will use units like microfarad, nanofarad, picofarad. You won't see scientific notation. So the closest one to convert this would be nanofarad, which would be 10 to the minus 9. How would I get 10 to the minus 9? Well, if I divide 10 to the minus 8 by 10, I'd get 10 to the minus 9. But in order to divide that by 10, I have to reverse it by multiplying the other part by 10. Right? You're basically doing nothing. You multiply by 10, divide by 10, you've done nothing. But multiplying the left side, or the 1.97 by 10, you get 19.7. Dividing the other part by 10, to the minus 9, you get nanofarad. So often when you're asked to solve a problem, you're going to be told, give the answer in microfarad or nanofarad or picofarad, because that's how it's typically used. So you see here's an example of working through the calculation. You see how this dielectric constant enters into it, the 3.7. You put material in there with larger dielectric constant, the same separation, same plate size. You can make the capacitance go up a lot. Okay. I thank you for watching all the way to the end.